At some parametric curves and ideas of this in the last video, and I wanted to give one example that actually comes from mechanics, and which we'll cover much more in detail. So we're going to begin that today, I guess, and we'll be back to pure next week. But like I say, it's just one example of where this parametric idea of looking at some sort of system is better than our typical Cartesian way of thinking about things. So let's put some XY plane on, okay, and say this plane here represents some space, and a two-dimensional space, but this can apply in the real world. And the situation we're going to apply is some projectiles, or some ball, or some cannon, or anything firing, starting from the origin. So it might be just shooting it from some place in a field, and we're going to set the place it starts as the origin, and then we're going to follow its trajectory, and we're going to say it's been shot with no spin or anything, so it's just going to stay in a two-dimensional plane. So it might go forward, and this is obviously happening in three-dimensional space, but we can just consider it as a particle moving in this two-dimensional plane. Okay, so we all know approximately what happens when you shoot a ball in the air, or a cannon, or you hit a golf ball perhaps. It follows this sort of path, okay, and it's heading in this direction. This is our y, and this is our x, where x is like the horizontal distance and y is our vertical distance. So we know that initially from the origin it's got some velocity, okay, so that's its initial velocity. Because velocity's got a direction, it's always, in this case, tangential to the curve, alright? And the reason parametric equations become useful here is because, one, you try and model this using Cartesian coordinates. What do you think if we take a point here? What's the relationship between x and y? Okay, you can try to figure that out, and that's in terms of some other constants we know. Bear in mind, we don't know what this turning point is, we don't know what this intersection is, we want to find that stuff out. So we've got this initial velocity. What's so useful about projectile motion, and this is when the parametric curves come in, is the movement up and down in the y direction decouples from the movement in the x direction, and this is true really for all sort of, if two forces act orthogonally to each other, perpendicular to each other, they have no components in the direction of each other, okay? So, and this is true in this sort of situation as well. And as I say, when we look into mechanics, we'll look much more into projectile motion, but this is just an idea. So in the x direction, we know our initial velocity is this velocity, but in this direction. So to put it in that direction, we have to move it around this angle cos theta. And if you use some trigonometry, you can see that the velocity we get is I've called this v. I'll call it u. It's a bit more intact with our Suvat equations that we'll see later. So anyway, so we get u cos theta. So that's our velocity, and we are now going to write this. If we're looking at the horizontal distance, well, we're going to assume no air resistance, so there's no forces, there's no loss in energy, okay, as this particle's moving, which means this velocity is constant. So x has u cos theta in the horizontal direction at any point. That's its velocity. So then we just use our basic formula. Speed is equal to distance divided by time. So distance is equal to speed multiplied by time. So that is our x distance, alright? So you can see where this parameter t is starting to come in. Bear in mind, theta is a constant, it's not some variable, we know the angle theta to the velocity. Okay, so y is equal to, and we're going to use the Suvat equation here. And I've got a little short video introducing the Suvat equations if you want to check out the short videos playlist. They release sort of every few days or whatever, and it's just some extra content alongside the A-level math, A-level further maths, and sequences series, and the R videos. So yeah, be sure to check that out if you've never seen these Suvat equations. But essentially, one of them is that the initial velocity multiplied by the time minus half of the acceleration multiplied by the time squared is equal to displacement. And in the y direction, our acceleration is minus g, and the reason it's minus is because our velocity is pointing upwards, so if our acceleration is in the opposite direction, we have to put a negative sign on it. Okay, so our initial velocity in the y direction is u sine theta, and again, a little bit of trigonometry, we want to move this around here, you'll be able to see that, our times t, and then we've got minus 1/2 g t squared. Okay, so now we have a set of parametric equations for x and y. So if we want to find a coordinate x and y in space, right, so we want to find what, when we get to this point x, what's y? Well, we can put that in for x, solve for a time t, and then put t into this equation for y. And that's nice and simple. What I can do is use these equations to try to show you the Cartesian form that we'd get. So t from equation 1 is equal to x divided by u cos theta, and we know u is non-zero, and cos theta will give us 0 when it gets to, if the angle theta was 90 degrees, but we're considering motion really where theta is greater than 0, otherwise we're just like rolling on the floor, and less than 90 degrees, because if it's 90 degrees it's just going straight up in the air. That's not very interesting motion. We're not going to consider that with projectiles because there would be no x component, so that would just be pointless, so we're not doing that, so we don't worry about that, and we can divide by cos theta. Okay, and then we substitute that into the second equation, and we get y is equal to u sine theta t over u cos theta minus 1/2 g x squared, okay, because we're substituting t squared, over u squared cos squared theta. These u's cancel each other out, and sine theta over cos theta is tan theta, so we get tan theta t minus gx squared over 2u squared cos squared theta. And you can see this equation for y in terms of x is quite complicated, and sorry, there's no t here, I don't know why I've put that in. T is equal to x over u sine theta, so there should be an x here. Anyway, so now we've got our equation y in terms of x, and you can see if we just tried to derive this straight away without introducing our parameter, I mean, it would be virtually impossible. Probably could be done, but you wouldn't want to give it a go. Then it's much easier to do it the way we did it. So hopefully this gives you an idea of why we use parametric equations and what their uses are, and also gives you a bit of a taste for the mechanics that's going to come up later on. So yeah, as I say, if you haven't seen the Suvat equations, be sure to look at that, my videos on that, and Yeah, and if you didn't see the first video on parametric equations, check that out. If you did enjoy this video, please be sure to like and subscribe, and I hope to see you in the next one.